Fahad? Go ahead. It's okay, you can think.
Metal is a substance which has a free valence electrons, like a sea of electrons.
Sea of electrons, that's one way. But would you say that to the science of metals, which is metallurgy, which is actually my original degree, has existed since 9th century or older, right? Ages used to be, in humanity, we have named our ages based on which metal did they have, right? I don't think they were thinking about valence electrons 2000 years ago, right? So it's shiny, right? There you go. Ductile, if you can stretch it, it can have elastic properties. So, it's shiny, it conducts electricity. That's one of the most fundamental things, right? If you put electricity through a piece of metal, it will conduct it, right? So these are all these properties. Now, when I did my undergraduate degree, the way we used to define metals in my solid state physics class was kind of similar to what Fahad did, which is a metal is a material with a Fermi surface. There is no other material which has a Fermi surface, and we will see what this actually means. So we'll talk about these things a little bit. So, and we are not going to go too much into it because this is not a solid state physics class, but the picture you have to remember is metal is something which has valence electrons which are easy to move. What comes between metal and an insulator? Since you worked with Johan.
Metal we have.
No, what is the material between metal and an insulator? Semiconductor, right? So semiconductor is kind of halfway. It does not exactly have valence electrons floating, but if you give some energy to it, just due to thermal fluctuations, it can have those. So those of you who are interested really need to think about energy bands and things like that, the energy gap. We won't go into all that. So, but the point is, we are thinking about, effectively, the problem we are thinking about is a sea of valence electrons. Now, why can you describe? So we have a sea of valence electrons. That's the first thing we are starting with. And secondly, the big assumption we are going to make is we will describe valence electrons as an ideal gas. That's a big assumption. These are electrons. Why do we want to describe them as an ideal gas? This assumption looks big, but it's actually not too bad. Chandler also talks about this. You should read it. The reason why this is not a crap assumption? You can pick up your. Kinjal and Kiet get the prize for using the maximum number of papers. This time, Kiet. You even gave me like extra empty sheets, which I took off for my printer. So good thing you give it to me in like, good thing you're not sending your PDF.
Did Aiden use the minimum number?
No, Aurelia had the minimum number. I think. Aiden and Aurelia are tied for the minimum number. Yeah.
What's the fun penalty per paper?
There is no penalty. So why is this not a bad assumption? Is first of all, the Coulombic interaction that the electrons are experiencing. How does a Coulombic interaction decay as a function of the distance r? 1 over r, not r squared. That's force. If it was 1 over r squared, then this argument won't work because 1 over r squared dies off quickly. 1 over r is actually kind of never dies. You can go and read articles by Feynman about self-energy of electron and things like that. This is a whole problem. So 1 over r is very, very slowly decaying. It just persists and persists. So if you go out to very, very long distances, 1 over r at a very long distance, as r becomes very large, persists and decays super slowly, right? So whether you are here or whether you are here does not make much of a difference. They are kind of similar. Okay, and I'm not going to write this all down in words here because then I'll be just stuck here. But so this 1 over r potential decays very slowly. That's one reason. So it's kind of like a constant field when you're very far out. If you're in thermodynamic limit, lots and lots of items. Okay, and secondly, there is also shielding of the core electrons, right? So this is interaction due to the valence electrons, and the core electrons are mostly shielded out, right? The nucleus is shielded out, the core electrons is shielded out. So shielding. So I'm not going into too much into detail of why this is a good argument, just trying to give you some intuition. Shielding of core electrons. So basically, it's an okay idea to represent the valence electrons as an ideal gas. That's the second key thing to keep in mind today.
How does shielding explain? I don't get where the ideal gas assumption is. Like, how
So
does
the most important thing for the ideal gas assumption is that the electrostatic potential between two electrons or any charge thing in the system. Actually, let's start with the shielding. So you have core electrons which are moving around, right? And you have a nucleus. So the net effect as you go out larger and larger and larger distance is a very small point charge, right?
Correct.
Right? And as you go to further and further distances, this point charge in the center is getting shielded by the electrons. And as you go further and further out, while you still have some charge, and it is still having an effect, whether you are here or whether you are here is immaterial.
But for an ideal gas, you don't assume any potential between the particles, right?
So there is a potential here, but assuming a potential of
So wouldn't you want something
no
fast-
potential, no
faster
potential is the same as a constant potential.
Fair enough, but you'd want a decay that's potentially faster than 1 over R.
No, then there is a problem. Then you have to worry about where you are landing.
Because otherwise you're saying that as they go some distance apart, they're still interacting with one another, which you don't see in an ideal gas. Should
They are
be-
not interacting. The interaction would be true. So you and I would be interacting with each other if you are sitting here and I go to Bethesda and I'm feeling something about Vedant, and then I move 1 feet. And if what I'm feeling about Vedant changes, then I'm interacting. But here the point I'm making is that I'm sitting in Bethesda and you are sitting over here. I'm feeling something. This potential is something which is being experienced. But whether I move a little bit from black to red does not make a difference.
That's fine when you accept the 1 over R argument. I'm saying that it's not clear to me why 1 over R should be, because your
1 over R arises due to the nature of the Coulombic interaction.
No, Coulombic
Fine.
interaction is fine, but with regards to an ideal gas approximation, because what if we were ideal particles, whether we're here or whether you're in Bethesda, we should feel the same.
You're talking about here versus Bethesda, and I'm talking about moving in Bethesda.
Wherever you move, it doesn't matter.
No, it really does. It really does. You have to think about thermodynamic limit. This field that is being experienced, you're talking about 2 electrons at the same time, and I'm saying that you are going to experience the electrons in the mean field picture. There is not just 1 electron. There are so many electrons that you effectively have an overall field that is decaying slowly. Go ahead.
Does that just, so is it like an ideal gas with the energy levels just shifting?
Yeah,
up or down?
that's all there is. Instead of 0 energy, you have a constant energy. That's all there is. And again, you're not thinking, you're fixating on 2 electrons at the same time. What I'm saying is there is 1 electron experiencing a C due to shielding that is coming from every other electron. It is just 1 constant field, which is very, 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 very slowly changing. That's the point. Think about it more and read Chandler's. Go ahead.
You said 1 over R squared is decaying too fast,
Yeah.
but 1 over R is just fine
Yeah.
for ideal gas assumption.
Yeah.
Can it be proven without using trust me bro argument?
What argument?
Trust me bro.
I don't know. Trust me, bro. I thought it's some like complicated Indian or Russian name. Oh, you can calculate the self energy of an electron, and you can show that if it was 1 over R leads to a divergence in the self energy of an electron. If you write down the self energy of the electron as 1 over R to the power n, you can show that if n is more than 1, it converges. If n is less than 1, it diverges. So it exists for a reason. And 1 over R is universal, right? It's not just electron. It also happens for big gravitational particles, right? So it's kind of universal. Vedant is very unhappy, but I think he will become happier when he goes home and thinks about it. Is everyone else also unhappy?
I mean, it's one of those things where like, does it actually work? I mean, I guess it does.
That's the thing with all models in physics, right? As physicists, we assume spherical cow. Does it work? Well, if it's agreeing with experiments, it's a good model, right? If you really want to, we make assumptions, we try to fit it to experiments, and if it's giving a good result, then we're like, okay, the assumptions are not that bad. So we are, for example, we are assuming that the electrons are completely independent of the atoms. That's already a bad assumption, right? If you have p electrons or d electrons, that's also going to fail. We're going to make more assumptions. And so we are making a ton of assumptions, and yet it works quite nicely compared to experiments, which is the beauty. The third assumption we are going to make is that the electron-electron interaction, and this is really a consequence of the shielding, and the electron-ion core interaction is much weaker than quantum statistical effects. And again, because there are so many electrons, if you try to apply this model to 2 or 3 electrons, it's not going to work, because then you will have to think exactly, you will have to go to Vedant's argument, and you would rather like to have something which fastly decays. So two things are completely oblivious of each other. But since you have so many of them, the presence of an ion somewhere is masked out by all the electrons that surround it. Okay, it's much weaker than quantum statistical effect. So these are the three assumptions we are making. We are saying that a metal has valence electrons, which is true. That's easy to move. We are assuming valence gas is an ideal gas. I tried to give you some intuition into why that is true. At least one person got very upset, but that's good. We are alive. And that electron-electron and electron-ion core interactions are much weaker than quantum statistical effect. So yeah.
How's the system in trouble? Like your collisions don't play any role on affecting.
It's like ideal gas, right? So same. Life is easy. So I'm going to recap an equation that we derived last time. So before I do that, let me draw what happens to the electrons, right? So there are energy levels. As you pump heat into the system, the electrons can go from ground state to excited state 1 to excited state 2, right? That's what happens. They keep jumping more and more. And if this is energy level J, last time we derived an expression for the average occupation number for Fermi-Dirac or Bose-Einstein. So we derived a fundamental, very generally valid relation, which looked like 1 over beta epsilon j minus mu and 1. So which one should have a minus sign before the 1? Michaela? Bose-Einstein. Why? Condensation, right? That's the only one that's going to diverge. So that's the easiest way to remember. So we are going to use this. Let's call this equation number 1. Since electrons are fermions, we are going to be using the plus sign. We are going to be looking at, so today, we will use ideal gas of fermions, which means that average occupation number Nj is 1 over e to the power beta epsilon j minus mu plus 1. Okay, this shows up a lot in physics. And in chemical physics, its name is, we use the symbol capital F as a function of epsilon j to denote it, and it is known as the Fermi function. Let's try to plot this function. So we are talking about, so these have all energies, right? Maybe the ground state has some energy, half h cut omega, then the excited state has some higher energy, so on and so forth, right? And for bosons, we discussed that the mu can be at max at the ground state level, right? But fermions, that's not true. Mu can be anywhere. There is nothing that is blowing up. So let's try, and let's call this equation number 2. Let's try to draw equation number 2, Nj, or f of epsilon as a function of epsilon. And what I'm going to do is to draw it first for t is equal to 0 or beta is equal to infinity limit. So 0 temperature, I want to draw f of epsilon versus epsilon. Okay, so as beta tends to infinity, what happens to f of epsilon? If beta tends to infinity and epsilon is smaller than mu, then e to the power infinity multiplied by a negative number is 0, right? So you have 1 divided by 0 plus 1, so that's 0. If epsilon is more, so if it's 1, sorry, yeah, 1 over 0 plus 1. So at this in this limit, if beta tends to infinity and epsilon less than mu, then f of epsilon is basically tending to 1. So we plot the value of, we call this mu, but the particular value of epsilon. And if epsilon more than mu, then this thing is infinity multiplied by a positive number. So 1 divided by infinity plus 1, or 1 divided by infinity, which is 0, right? So the Fermi function looks like this. Now you might think this is so boring. Who cares for Fermi functions? But all of deep learning and machine learning is just about functions like this, nonlinear activations. That's it. You won't use this in a code because this is, well, actually this function is nice. It's differentiable as a function of epsilon, right? It's a really powerful. So all of machine learning basically uses a step function of this form or the other, and then they write papers arguing over which step function is better. So this is how it looks like at t is equal to 0. So what does this mean? It means that physically this means that at 0 temperature, if this is my Fermi level, so mu is known as the Fermi level in energy, everything below the Fermi level will be occupied. Everything below and up to the Fermi level will be occupied. And here I have put in 2 electrons in a level because I'm accounting for spins. Go ahead.
Does mu have to be at a particular Fermi level?
Mu is the Fermi level.
Sorry, does mu have to be on a level, or can it be between?
Mu can be between, but then you start getting to a semiconductor. So for metals, mu is actually at the energy level from what I remember. Now, what you're asking is how does it really compare to the band gap, right? So not the band gap, but the quantum of energy. So that depends on the frequency, right? So if this h cut omega is very, very small, then it becomes very likely that mu is going to intersect with one of the energy levels. If h cut omega is high, then it's likely, maybe it does not. So we have to think about the frequency. So it will change material to material, frequency to frequency, right? So it could be different. So it could lie or it might not. But the point is now.
For many physics, like the energy levels are so close anyway. Right?
Exactly. So as you go to higher, more and more number of atoms, the energy levels start to get tighter and tighter. So the point is, once you go to energies above mu, the occupancy drops to 0. So here there is no occupancy. Here there is occupancy of 1. Everything is going to be occupied. This is the picture. Now we put in some temperature. This was t is equal to 0, right? So let's draw the same thing. For f of epsilon versus epsilon, as t starts to become slightly smaller than 0. No, what am I saying? T starts to become slightly larger than 0. What will happen to f of epsilon? Physically, what do you expect? I drew this picture over here. Physically, you expect that these electrons that are on the top will jump, right, and move to the next level. Will these electrons in the bottom be able to jump? No, the gap is so high, right, that it's like crazy. It cannot jump above. The ones close to the Fermi level will be able to jump. And some of them will, so it will look something like this. So if this is mu, these ones will still be fully occupied. But as you get closer to mu, maybe you will see that some energy levels below mu are half occupied, some energy levels above mu are half occupied, and then as you go further up, again, it drops down to 0. So what this means, and you can do this, it's easy to plot this function in Mathematica or wherever and see how it looks. But basically, if this was my mu value, it will start to look, it will stay 1 for low enough energies, and then it will start to go down, and it will look like this. Okay, so this is how the Fermi function looks. If you make the temperature higher and higher, the broadening, the half width becomes, the width of the function becomes more and more over here. So this width increases with T. So the key physical picture here now is that when we are talking about the capacity for heat due to exciting electrons, it's only these electrons that are going to contribute, okay? Only these electrons contribute to heat capacity. The other electrons, the ones which are deep within the Fermi sea, they are not going to do anything because they cannot get excited due to thermal fluctuation, right? That's the point here. Any questions? Okay, so let me draw this picture, the second picture once again, and we will work with this one. So we have F of epsilon versus epsilon. Which looks something like this. And the half point where it goes to half. So this is 0, this is 1, this point is mu. And what we would really like to do is to figure out how many electrons are in this shaded area. And that will allow us to calculate the heat capacity. So I'm going to do this in a very intuitive manner, okay? The proof for this, and I will show you how the linear dependence comes out quite naturally. There is a more rigorous way of doing it. Chandler does that. So Chandler exercise 4.10 tries to walk you through that rigorous proof. And the book by Rife or Rife, whatever you want to call it, which is Statistical and Thermal Physics, also does it. And this very rigorous proof is known as Sommerfeld expansion. That's 3-4 pages of only algebra, and you have to keep working through algebra. And you will see how the full thing comes out, but we are not going to do that. The intuitive proof is actually quite nice because if I did that, you will forget it anyway. The intuitive proof, I think you will remember for a while. So what do we want to do? What do we want to do? We want to think about the energy levels at 0 Kelvin. We know that if these are my energy levels, and let's say this is the epsilon is equal to mu value, and same energy levels at T more than 0 Kelvin. So we know that at 0 Kelvin, in energy, any energy level, you will have 2 electrons per level corresponding to the 2 spins, and you go up till here, and then it drops to 0. As you go to finite temperature, the deep ones are going to stay the same. But as you get close to the Fermi level, you will see some excitations, and they will go up. Okay. So it's these electrons that we are interested in. These are the excitations possible close to energy equal to mu. That's what we need to calculate. So let's say there are N1 such electrons. Let's say there are N1 such excitable electrons. I have assumed an ideal gas, right? If I have an ideal gas made up of N1 electrons, what is going to be the internal energy of that ideal gas? Absolutely correct. So U of an ideal gas made up of only excitable electrons is going to be 3/2 kT multiplied by N1, right? Not the N. The total number of electrons does not matter because they are just sitting. They're not going to do anything. It just does not matter. Is equal to 3N1 kT by 2. And what I want to do from this is to calculate the CV. How do I get the CV from U? what I really want to show you, this I mentioned in the first lecture of this class, right? I would like to show, let's be more inclusive. We would like to show that CV is proportional to T. If you want to show CV proportional to T, what do you expect U to look like? Proportional to T square. U already has a T term. So what does it leave for us? We have to show N1 proportional to T, that the number of excitable electrons is proportional to temperature. If we can show this, then we are set. Then we have an intuitive idea for why is the heat capacity linear in temperature. If that does not make you happy, then go and read up Sommerfeld expansion. The first time I taught it, poor students, they had to suffer through it for 3 lectures. And then John Weeks told me that he never does that. He also went through that experience like 30 years ago, in the days and time of Sommerfeld. No, John is younger than Sommerfeld. So how should we show this? The proof is kind of nice. It's semi-proof, it's a back of the envelope. We are talking about Fermi, who was like the guru of back of the envelope calculations, right? He used to be the king of back of the envelope calculations. There are Fermi problems, right? Inspired by him. So this is what we want to show. How to show this, that the number of electrons, number of excitable electrons close to Fermi level is proportional to T. So you could do it very mathematically. You have the Fermi function, right? You can write down the definition of the width and do it, completely analytically, but we can do it simpler way. So let's draw the f of E plot, f of epsilon plot. So we have f of epsilon versus epsilon. And let's draw the value. This is mu. And we know this is a curve that goes like this, then drops here, and then goes like this. So let's see if I can do it purely geometrically or not. Let me do it a bit more mathematically. So we want to calculate number of electrons in a given energy range d epsilon. Okay, so how would that look like? So we are interested in n of epsilon multiplied by d of epsilon. What is this going to be? This is going to be proportional to f of epsilon, right? The average number of particles you have in a given energy level multiplied by d of epsilon. What else do we need to have here? What is missing here is something you saw in phonons. Yes, but what is a fancy name for degeneracy? Density of states. Density of states is nothing but a fancy name for degeneracy. Okay, so we have to multiply by density of energy levels. That's what is needed. And then we need to multiply by 2, which is per spin, because electrons are spin. But if you don't like the 2, that's okay. It doesn't matter. We are just going to do proportional things. So n of epsilon d epsilon is density of states, DOS, or degeneracy of energy levels. And this is basically average NJ, right? So in any given energy level, you can calculate what is the average number of particles, but then you also need to know how many such energy levels can exist, right? How degenerate they are. So this is 2g of epsilon, f of epsilon, d of epsilon. So close to Fermi energy, we are thinking about energy which is in a tiny range, right? We are not talking about finite temperatures. We are talking about small non-zero temperatures. So close to epsilon, around mu, we can say that therefore n of epsilon d epsilon is approximately 2 multiplied by G of mu, the density of state at the Fermi level. Okay, so we approximate it. We say, well, it's not going to change drastically. Let's approximate it. Multiplied by, Omar, you look very sad.
No, fine.
Are you still sad over that exercise problem? You can argue with me
I'll
later.
finish. No,
Yeah.
no, it's fine, it's fine.
Okay. Are you sad because you're in class? No, no
I'm not
comment.
happy.
Huh? Oh, what was that? What was that?
I think that's it.
You're just because Donald Trump is in jail or going to jail, you cannot do that today. Is he in jail now? No, I don't know.
He's in rich man's jail.
Even I don't think he's even there, and there won't be a photo or anything like that. Also, if there's a photo, you don't know whether it's a Dali photo or it's a genuine photo, right? Who knows? I mean, our provost sent out an email. Did you all get it? Encouraging the use of ChatGPT in UMD courses.
I don't check those emails.
Yeah, but as a faculty, we get these things. And I'm like, do you have any idea what you're even talking about? I think I think in physics and many subjects, I think we are safe, but a lot of subjects you to ChatGPT where you just have to write essays. How are you going to judge people? It's unless you're having a one-on-one interaction. But if you have a 200 student class, bizarre times.
Just the complexity of the problems.
Huh? Yeah, it will be. I think in-class examinations and oral examinations and things like that, they will come back. I don't see any other way. But then you will have. We are approaching the matrix, right? We'll have things in our head.
You
Huh?
think one sense like Turnitin could find a way to tell someone wrote about ChatGPT?
Oh, that's a good point. So there is a professor here, Tom Goldstein, in computer science. He has watermarked for ChatGPT. So basically, he has found they trained on a bunch of sentences from ChatGPT or normal sentences. And if you do machine learning, so you're doing machine learning on machine learning, and you can see trends. Like ChatGPT will say, you can see things like it will try to do things like this, instead of just doing this, and you can come up with something like that, and that has 90% accuracy.
So that's if someone were to copy whatever is written directly and put it in.
Yeah, you can start breaking it. But yeah, let's come back to Fermi.
Remove that ChatGPT.
You will get it. So let's think about this. So we have to calculate N1, which let's come back to our N1, which is the number of electrons which are lying in this energy range, right? This is going to give us N1. So N1 is going to be integral of N epsilon d epsilon as the energy goes from mu minus, so this value is mu minus kT by 2, and this value is mu plus kT by 2. Why is it kT minus kT by 2 plus kT by 2? Because you can go and mathematically calculate the value of the Fermi function. And basically it is the value at which there is a 1 over E difference, that's where it comes from. So this is integral mu minus kT plus 2 to mu plus kT by 2.
Can you just go over where we got the N1 lies in that KT interval? Well, are we just looking at?
Yeah, so we are saying that f of epsilon tends to 1 as approximately tends to 1 as energy becomes smaller than mu minus kT by 2. F of epsilon approximately tends to 0 as epsilon becomes mu plus kT by 2, and which is really what we are doing to prove this thing. That is the only idea. This, I am just throwing it out there. If you want to see this, you have to go and calculate the Fermi function for different values. For small temperature, this is going to be valid. The way to do it is to do a Taylor expansion of the Fermi function, and you will see if this comes out. So this is an integral mu minus kT by 2 to mu plus kT by 2 of n epsilon d epsilon, which is itself 2 g mu f of epsilon d epsilon. G mu can come outside the integral, so this becomes 2 g mu minus kT by 2 mu plus kT by 2 f of epsilon d epsilon. So we have to prove that this quantity in the integral is approximately kT. How do we do that? Yeah.
I don't even see why G of epsilon is just independent of.
Oh, G of epsilon is not independent, but you're talking about such tiny changes. yes, G of epsilon by 2 is very different from G of epsilon, right? But is G of epsilon minus KT different from G of epsilon if KT is very small?
But
Basically, we are talking about small KTs. So the density of state varies slowly with KT. That's the idea. Okay,
why is that? Why is that?
because KT is small enough. It's a circular argument. We're just talking about small temperatures. There exists. If you were doing real analysis, where is Margot? Margot, do you know the book by Rudin? Real analysis by Rudin?
I don't really do real analysis.
No? Oh, good for you. It's terrible. But it is full of arguments like this. My student Luke, you know him, right?
Yeah.
Luke loves Rudin. Huh? Do you know Rudin? Have you studied it? It's a terrible book, right? But there are 3 Rudins. Do you know that?
Yeah,
You are probably talking about the baby Rudin.
yeah, this baby.
Baby Papa Rudin and Grandpa Rudin.
Yeah.
And they are really terrible. Baby Rudin itself is very bad. That's when I stopped being a mathematician. So baby Rudin is full of this. So you tell me, you're asking me, why should it be true? And I'm giving a circular argument. I'm saying that if the temperature is small enough, this will be true. So if we really want to get there. Then there is a physical argument that the density of state themselves, it increases with energy. And so, okay, actually, let's think about it. How does the density of state increase with energy? What is the dependence of G of epsilon on epsilon? Does anyone know the answer? You can just say it if you know the answer.
He said, what's G's defense? That's what.
Huh?
Could you ask the question
Yeah,
again?
could you?
How does the density of state G of epsilon depend on epsilon?
That's something they have.
So yeah, it doesn't matter how it depends on epsilon. G of epsilon is a smoothly behaving function that it does not. So
Yeah.
G of epsilon is constant of a
Yeah.
small epsilon.
So can you think about, and we are again going a bit far from statistical mechanics, but if you solve, you can solve for G of epsilon for particle in a box. And you will see it's like a square function or something like that. So it's a smooth function. It's not a funky function. Okay, happy Kenzo? But now let's get back to this. Now we have to calculate this integral. Okay, let me write it down on the next page. And let me draw my, so what we want to do is to calculate N1 is approximately 2G of mu minus KT by 2, mu plus KT by 2, this thing, okay? And we have to calculate this integral. And in order to do this, I'm going to look at the f of epsilon versus epsilon plot. Once again, this is my mu, and I know it goes something like this. And what I'm saying is that this value where it becomes it shows appreciable difference from 1 or 0 only over a range of KT. Okay, that's the point here. So given this figure, how do I calculate that integral on the top? And this is 1, this is 0. Any ideas? What is the cheapest way to do it? Your hint is Pythagoras.
Assume this is a triangle.
Assume it's a triangle. Assume it's what type of triangle? Right angle triangle. What is, and do we know the area of a right angle triangle?
No.
Why not?
1/2 base times.
One half base times height, right? So assume this is a right angled triangle. So if this is the base and this is the height, then the area is half multiplied by base multiplied by height. What is the base here? KT. What is the height here? 1. So what do we get? N1 is approximately 2G mu half KT, or N1 is approximately G mu multiplied by KT, or N1 is proportional to temperature. Okay, so if N1 is proportional to temperature, then the energy of an ideal gas made up of only excitable electrons at low enough temperatures is proportional to 3/2 kT multiplied by temperature, or proportional to temperature squared. And the low enough temperature is very, very important. Okay, this will break if you're not at low enough temperatures. You will have to worry about not taking G of epsilon outside it, right? You will have to worry about how G of epsilon changes and things like that. So this is what we have. If U is proportional to T squared, therefore CV is proportional to T. CV due to electrons. So this was a hand waving, but it's still a nice proof. It gives you the basic picture. And physically, what will you remember in this? What I did so far today is in phonons, the excitations are happening at any energy level, right? Why was that the case? Why is it that for phonons, we could allow excitations at any possible energy level? And why is it that for fermion, we had to look at excitations only at the top? Someone who has not answered. Sophia, what do you think? For electrons, why did we make all this song and dance that we have to worry about excitations only over here? Why could we get away with it for phonons? If I drew the energy levels for a phonon, would it look like this or would it look like something else? How many phonons can you pack into one level? Your hint is bus in India. You forgot my intuition. In one energy level, you can have only 2 electrons due to Fermi exclusion principle. You can pack in as many phonons as you want, right? That's why I keep saying the bus in India. You haven't, if you have not been to India, then you don't know my motivation. Angel knows what I'm talking about, right? He's laughing, but it's true. It's like the bus is never full. You can, yeah, or local trains. Yeah, oh yeah. You can keep packing one more person. Motorcycle never has enough people. You can always put in. I have definitely ridden 5 people on a motorcycle. It's true. It's true. I have done it. So in phonons, so this is for electrons, right? You can only have 2 things in one energy level. In phonons, you can keep packing in as many as you want. So in phonons, we don't have to worry about things that are close only to some level. In phonons, if you give an excitation, it just goes to the next energy level, right? That's why for phonon, we did not have to do this math. Is this clear? For electrons, we had to specifically focus on the Fermi level. And for phonons, we could not do that. So this is how we get. So overall, what is the picture? This is the last thing about heat capacity. Now we move to photons. So we just showed that CV due to phonons at low temperatures is proportional to T cubed. CV due to electrons at low temperatures is proportional to T. CV overall then is proportional to AT plus BT cubed at low enough temperature, ignoring electron phonon coupling. If how the lattice atoms are moving decides how the electrons are jumping, which happens in a lot of materials, then this breaks down. But otherwise, this behavior of CV, you can fit in almost all experimentally measured CVs by using this. Okay, so this is very, very powerful. Any questions about this? No questions, Alex?
Maybe just include prerequisite of living in India experience for this class.
Huh?
And prerequisite for this class, living in India experience.
No. It's not required. You can watch Bollywood movie and you will see it. Vedant can give you suggestions on that. Right? Why, you don't like Bollywood movies?
No, I do, but I don't recall one where there's a bus full of people.
Come on.
Off the top of my head.
Yeah.
Someone-
So let's not deviate. So the next thing we are going to do is our final application of non-interacting systems, which is a gas of photons. Okay, this is the same, it's also known as black body radiation. After this, we will move to interacting systems. So I don't think I will finish this today. I will just start it. And then I will finish this next class. And next class itself, I will move to interacting systems, where the math gets a bit different. For interacting systems, I recommend you brush up on conditional probabilities and Bayes theorem. Okay, we are not going to use Bayes theorem exactly, but it will help you if you look up that. So, but in general, brush up your probability densities. Yeah, so we will be using a lot of complicated probability distributions, but that starts next class. So the final application of two non-interacting systems in this class is a gas of photons. So gas of photons. And this is to be distinguished from what we did for electrons. In electrons, we had a finite number of electrons. Electrons don't just pop out of nowhere, right? Especially in metals. If you have some chemical reaction going on, then yeah, they can happen, right? But chemical reaction always has a cost. Photons, on the other hand, just keep showing up, right? There is no cost. I will draw the picture on the next page. So what do I mean by this? So I'm interested in an I have already posted a PDF article which goes over what I'm doing in great detail on the class website. Please go and look it up. It will be helpful before next class if you look it up. So an electromagnetic field in thermal equilibrium with its container. So it's going to look like this. We have a container. Which is really, really closed container. It has a very, very tiny hole from which you can study. You can kind of see what radiation is coming out of this. But otherwise, this is, apart from this little, very tiny hole, this container is insulated from rest of the world, okay? And the radiation that is emitted from this container has a name. Anyone remembers? Black body radiation. So how do we set up this container? So the physical way for doing this would be to make a cavity in a large material, evacuate the cavity from everything, complete vacuum inside it, okay? And then it has some volume V. Then heat the material to a temperature T, until thermal equilibrium is established. When you get to this scenario, so you have a big material in which you made a cavity, right? And you heat the material, and now you're interested in what is going on inside the cavity. So inside the cavity, what's going to be happening is that the walls of the cavity, the atoms in the walls of the cavity are going to be continuously emitting and absorbing radiation, okay? So atoms of the walls of the cavity will be constantly emitting and absorbing radiation. And this is electromagnetic radiation, and it's going to have a certain frequency, right? What would be the frequency of such radiation? Anyone has an idea? We don't know. In fact, that is the question. So if the cavity is fully isolated, then we cannot study anything. That's why we made this tiny hole. So it's like the tiniest perturbation we can make to see what's going on, okay? So what we want to do now is to look at the energy density of the radiation as a function of the frequency and see how it depends on temperature, okay? And I'm going to write down the results before we get into the math. And because what I'm doing seems like an intellectual exercise, but this is actually of profound importance. So we will show next class that U of omega, the energy density. So what is U of omega? So U of omega is average energy per volume, because we could have a bigger cavity, right? Per volume at frequency omega. Who here has done undergrad in physics? Do you remember? What is this expression? What it comes out to be? A very, very famous person derived it. His name was Max Planck. It's known as Planck's formula for black body spectra. And it's a beautiful relation, and we are going to basically derive it fully. I will make one assumption about density of state, like we did for Debye. Apart from that, it will be fully rigorous. And Planck's answer was beautiful. It looks like h cut omega cube divided by pi square divided by speed of light cube e to the power beta h cut omega minus 1. And now, since you are all experts in quantum statistical mechanics, just like Michaela helped us out a little bit earlier, why do we have a e to the power beta h cut omega minus 1? Because photons are bosons, right? That's, you already have a feeling for why this shows up like this. The other stuff is basically normalization. So it's a beautiful relation, which is ridiculously accurate. It's ridiculously accurate. You can do one more thing, and you can now calculate not just U of omega, but you can calculate the average energy per volume at any frequency. How will I do that? In order to do that, I will have to do 0 to infinity d of omega multiplied by U of omega, right? If I do this integral, then anyone knows what is the name of the law we get? Stefan-Boltzmann law, right? So then we obtain the Stefan-Boltzmann law. And that one is even more peculiar. It has like bizarre constants. That turns out to be pi square by 15 kb to the power 4 h cut cube c cube and the famous t to the power 4 dependence. So t to the power 4 dependence, probably somewhere, some of the neurons are clicking that you have seen it. If like me, you come from India, then even for the engineering entrance exam, you probably mug this. Some people are nodding their heads. But it's a beautiful relation. Look at all the constants that showed up here, right? It's like magical. You have pi, you have Boltzmann constant, you have Planck's constant, you have speed of light. I don't think there are many other relations in physics where all this many fundamental constants show up in one relation so naturally. So, huh?
How about the fine structure constant?
Oh, then who knows what is that? When you start going to fine structure constant and the number of, people call it the zoo of particles, right? Then you start losing faith in science. You know, it's like, what is the point? No comments, you know. So we are going to prove this. And I want to make a point. Why is this is all so important? Because there is a big experiment that is still going on, which is known as COBE or COBE, I don't know how to pronounce it, which is Cosmic Background Explorer. So you might think, why should I care about this bizarre setup where I make a material, make a cavity, let it come to thermal equilibrium? This is a good model for many, many things in the world, including the early universe, where we all come from, right? So when people derive these expressions, and this Cosmic Background Explorer is able to actually measure the energy at a particular frequency, it is able to measure small u of omega. And these things fit it to like 15th decimal place. So if you read the PDF that I posted online, which is from a professor at in applied math and theoretical physics at Cambridge, this professor makes the comment, and I forget what exactly is the point of the comment, but the point is I will tell you why I forget. He says, this formula fits the known experiments up to 10th decimal place. And then he says either which is the best proof that God exists, or he says which is the best proof that God does not exist. I forgot which one he says. But basically, for this professor, this was like a religious experience, that you derive something like this, and then you measure something in a complicated instrument, and you get a fit 2 to 10th decimal place, right? Which is incredible. So I'm going to stop here. Please go through that PDF I posted, because we are going to use a little bit more quantum mechanics next time, not too much. And we will derive this, and then we will start with interacting systems.